So now let's look at a similar problem, but this time with the intersection. So as always, let's draw some diagrams to see if this is even true. So let's look at the two examples where all three sets share something and all three sets don't share anything. Starting with the first one, A intersect B. Well, that's going to be the area we're interested in that looks like this, right? The area where A and B both intersect. Fantastic. Then we want to take this area here and take away C. Take away any part of it that overlaps with C. Well, what part of the shaded area overlaps with C? Well, it's just going to be this middle part here. So we're going to want to erase it since we're not interested in it. So there we go. We're going to be left with this shaded area. Now we're going to look to find the same area on the right-hand side using this set. So using this set, what do we get? Well, we get A minus C, which is going to be all of A, not including C, right? So we're going to highlight all of A that is not going to be in C. Fantastic. We're not highlighting these two areas because they're obviously a part of C. Similarly, with B minus C, we're going to want to highlight all the area of B that's not in C, which is basically not going to include these two areas. So we're going to want to highlight this and then all of B. And then we're going to want to look at the intersection of these two shaded areas. So where do these two sections intersect? Well, it's not going to be here because A doesn't intersect with B here, obviously, so we can erase this half. And similarly, on the other half, B doesn't intersect with A here, so we can erase this part as well. So this is going to leave us with the same area as we found on the left-hand side. So this is going to be true for this case. What about the case where they don't share anything at all? Well, that's going to be that the left-hand side is going to be A intersect with B. So what part of this has A and B intersect for us to shade in? And the answer is none. No part of this has A and B share anything. And then, so what is nothing minus C? So you don't want nothing to intersect with C, so that's just going to be nothing, right? So we leave this blank. So hopefully we also get a blank on the right-hand side. Well, let's look. A minus C is going to be everything in A that's not in C, which is just in this case going to be all of A. And similarly, B minus C is going to be all of B that's not in C, which is also going to be all of B. Since neither A shares anything with C and neither B shares anything with C. Now we want to look at these two areas and see which part of them intersect. So which parts of these two sets intersect together? And the answer is none. So we actually need to erase everything that doesn't intersect with each other. There's no part of B that's in A and no part of A that's going to be in B. So there we go. We find that in this case, it's going to be empty on the left and on the right. Let's just try two more examples and then we can move on. Let's look at the case where at least two of the sets share something in common and the third set doesn't share anything in common. Right, so let's first look at if A and B share something in common and C doesn't share anything with A and B. So we find that A intersection with B is going to be this area right here. And then we're going to ask ourselves, well, what part of this area, this shaded area, does not share something with C? And the answer is none, so we just leave it as it is. What about the right-hand side? Well, the right-hand side, we're going to say A minus C, which is just going to be all of A, right? And we're not going to erase anything because no part of A is in C. And then similarly, B minus C is going to be all of B for the exact same reason. And then we're going to want to ask ourselves, well, what part of these two areas overlap each other? So what parts of B have A and what parts of A have B? Well, it means we don't want to look at this area because this area doesn't have any part of A and B. And similarly, on the left-hand side, we want to erase this part because no part of this has B in A. So we're going to find that, yes, the two areas shaded in are going to be the same on both sides. Well, what if instead we have B be the set that doesn't share anything and A and C share something together? Well, what are we going to find on the left-hand side? Well, A intersect B is just going to remain blank because there's nothing to shade in. No part of A and B intersect with each other. Minus C, well, we've shaded nothing and nothing doesn't intersect with C, so we still color nothing in. What about here? Well, A minus C is going to be this area here, where no part of A is going to be in C, right? And then B minus C is going to be nothing. There's nothing for us to shade in. So what are we going to find? Well, where does A intersect with nothing? And the answer is nowhere. We already know the answer that A intersect with the empty set is just going to equal to the empty set. So we're going to find that we need to erase the part that it doesn't have any part of B in it, right? That's what it means for for these two parts to intersect together. So we're also similarly left with empty sets, or sets that aren't shaded in, sorry, not empty sets, sets that just simply aren't shaded in. So we find that it's true in both of these cases as well. So this means I'm pretty confident in proving that this statement is going to be true. So let's do that. So to start off our proof, we need to recognize this is going to be an equivalence, which means that we have to prove the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. Why? Because logically, if they're equal, everything here has to be here, and everything here has to be there, which is exactly what a subset is. So how do we start the proof? Well, it's going to be a for all proof since we are looking at any sets A, B, and C. So we're going to start with a let. We're going to say let A, comma, B, and C be sets. There we go. Now we can get into our first case, showing the left-hand side is going to be a subset of the right-hand side. Okay, so to prove our first case, let's have a look at this, right? We want to start by saying this set is going to be a subset of that set. Or not by saying, we're going to start by trying to do that, right, with our proof. So how are we going to do that? Well, if we can say any element, and we'll just label any element X, that's going to be in this set is also going to be in this set, since X represents any element here, and it's going to be here, we've shown that all the elements in our first set are going to be in our goal set, which makes the first set a subset of our goal set. Okay, so how are we going to get from here to here? Well, let's have a look. What does it mean for X to be an element of this set? It means that X is an element of A intersect with B, and X is not an element of C. Fantastic, okay. Now from here, we have to somehow get to here, which means we probably want to get it so X is in here, and X is going to be in here. So what can we say? Well, we can break this apart further. For X to be in A intersect B, it means that X is in A and X is in B. There we go. Okay. Well, if X is in A and X is not in C, we know that X is going to be an element of A minus C. And since X is an element of B and not in C, then we know X is going to be an element of B minus C. And since it has to be both in both of these sets, we get our goal set down here. Yeah, this seems to make sense. So let's go ahead and put this into words. We start by supposing our representative element, X. We say, suppose X is going to be some element of our left-hand side, A intersect B minus C. Then, as we did here, we want to break down what it means for X to be an element of this set. It means that then X is an element of A intersect B, and X is not an element of C. Fantastic. Okay. Yeah, I'll leave that as it is. Great. And then we can say for X to be an element of A intersect B, it must be that X, or I'll write that in the next line, X is an element of A and X is an element of B. Fantastic. Now we can say, next, given X is an element of A and X is not an element of C, comma, X is going to be an element of A minus C, and similarly, given X is an element of B and X is not an element of C, comma, X is going to be an element of B minus C. Finally, since X is an element of A and X is an element of B, then X is both, then, actually no. We'll just say that a little differently. Sorry, the blue keeps rubbing out on the whiteboard. We say then X is an element of A minus C and X is an element of B minus C simultaneously, making X an element of A minus C, or not and, intersect with B minus C. And then we can say, thus, we can now conclude what we were trying to prove. A intersect B minus C is a subset of A minus C intersect with B minus C. So there we go. We've proven that the first case is going to, in fact, be true. Now let's try the second case. Okay, so to prove that the right-hand side is a subset of the left-hand side, we're going to apply the same strategy as we did for our first case. We're going to want to get from here to here, which means we're going to want to show that any element here, for example, y, is also going to be an element of this set. So how are we going to do this? Well, what does it mean for y to be an element of this set? This means that y is an element of a minus c, and y is an element of b minus c. Fantastic, okay. What does it mean for y to be an element of these two sets? Well, this means that y is an element of A, and y is not an element of C, and y is an element of B, and y is not an element of C is what this part over here means. Of course, the and just transfers over. So, since y, we can now say, since y is an element of A, y is an element of B, comma, and y is not an element of C, we can now conclude this, right? Or, since, actually, sorry, that's not very good. I can do a better job than that. Since this is going to be true, we can say, since y is an element of B and A, y is an element of A intersect B, and since y is not an element of C, that goes with this into this arrow, and they both go down here. Okay, it's a little messy, but I think that makes sense. So let's go ahead and put that into words. We start by supposing our element y. We say, suppose there exists some element y in a minus c intersect with b minus c. Fantastic. We can then say, then y is an element of a minus c, and y is an element of b minus c. There we go. Now we can break apart what this means, or actually we can put a comma and continue the sentence. We could say, so y is an element of A, and y is not an element of C, and y is an element of B, and y is not an element of C. I don't like repeating myself, and I think I want to be a little more explicit. So we'll say, so for y to be an element of A minus C, then y is an element of A, and y is not an element of C. And for y to be an element of B minus C, then y is an element of B, and y is not an element of C. So we can then say overall, y is an element of A, and y is an element of B, and y is not an element of C. Since y is an element of A and y is an element of B, y is going to be an element of A intersect B. And then we can say now that y is an element of A intersect B and y is not an element of C, comma, y must then be an element of A intersect with B minus C. Fantastic. Making this true, making A minus C intersect with B minus C a subset of A intersect with B minus C. So there we go. We've proven the first case and the second case are both going to be true. So all that's left now is to conclude that if that's true and that's true, this must be true. So let's go ahead and write that down. So there we go. That is going to be our conclusion. So we've now proven that this statement is in fact going to be true.